straightforward. All right, so before you do that, I would grab another blank warm-up section if you have one. Just so you can see what that A value is doing before I throw it into a word problem, or not into a word problem, into a locus problem. If I just give you the general graph y equals x squared, I'm going to draw a graph, general parabola, and I'm going to label it y equals x squared. Then if I want you to graph another one, and at home I really hope you're drawing these down as well, because again, this is going to introduce what that A value is doing, which is what we need today. What if I ask you to graph 2x squared? Not x squared plus 2. If it was x squared plus 2, it'd shift it up 2, right? Does anyone know what y equals 2x squared would do? It's not shifting it up and shifting it down. What do you think, Amelia?
Shifting it to left.
Not to left and right, because that would actually be, and I like where your head's at, that would be x minus 2 pointers squared, right? That would actually go to the right, or if it was plus, it would go to the left. So plus and minus is left, right, up, and down. Lydia?
Does it change the roots?
Change the what?
The roots?
The roots? No, it's actually going to stay exactly there. I like where your head's at, so Lydia thought maybe change the roots. What it does, think about like a hair tie, okay? If I was to put it right here, okay, and said this was my function, if I took this, and do you see how this would be multiplying the output by 2, right? Multiplying the y values by 2. Like if I plugged into 2 squared would give me 4, multiplied by 2 would give me 8, right? Do you see how it's taking the output and multiplying it by 2? So what I'm doing is if I multiply the y values, keep the x values the same, but multiply the y values, you see how it gets narrower? And if I multiply the y values by 3, it's going to get narrower, and I'm going to try really hard not to, Amelia. And if I multiply it again, do you see how it's getting more narrow and more narrow? Okay, so y equals 2x squared. So now the shape of the parabola is actually changing. If I did y equals, I meant to change that color, 4x squared, even more narrow. The roots are remaining the same, but the shape of the parabola is getting more narrow. Can anyone think about what kind of number could I multiply? Watch the hair tie. I know it's hair tie math, fun stuff. Okay, if I wanted the parabola to get wider. Not negative. Negative would actually, I like that. That's what a lot of people say. Negative would actually take it and flip it. Remember, negative x squared would make it concave down. So not a negative. Fractions. Good. If I gave you y equals 1/2 x squared, 1/2 x squared is going to be half that distance. Taking my outputs and cutting it in half. What would even be wider than 1/2 x squared? 1/4 x squared. So what this value out in front is doing, is it changing my roots at all? And again, these are rough sketches. They're not exact. But are my roots changing? No. Is it shifting up, down, left, or right? No. What it's changing is actually the shape of the parabola. What that's called is the ones that are greater than 1, that is a vertical stretch. The ones that are in between 0 and 1, those are compressions. And that's going to actually carry us all the way to the spring, because we're going to see this with trig functions. Sine graphs and cosine, we're going to stretch and compress them. All right, with that being said, then I need you to grab your packets and try to find page 95. This is where some of the page numbers just decided not to label. So there is, I think, all the way up to 93 if you have your yellow packet. If you don't have your yellow packet, it's totally fine. Again, plain paper will totally work.
Wait, you said what page?
95 is the last one that's numbered, or 93. I've got boxes of extras. Boxes. Here we go. Yes. All right. I know, it's a pain. All right, then you're going to flip. So you finally find that one. I know that I'm going to ask you to flip again. Do you see this one where it said warm up? Mm-hmm. This one was too straightforward. It was too easy. That's why I made it a little bit more challenging. Flip the page again. All right, now we get into the good stuff. Do you see how it says quadratics? Do you see how unfortunately my page numbers disappeared? Just stop numbering them. All right. With our quadratics, this is standard form. This is vertex form. But we're going to use vertex form because it's really the same thing to find out what our locus definition is. And our locus definition is all focusing in on that A value. So it's really focusing in on the stretch and the compression of our parabola. So just to recap again, we know to go from standard form to vertex form, we know we're going to complete the square, just like you did in your warm-up. If for some reason we wanted to go from vertex form back to completing the square, backwards, all you do is expand. So go back to standard form, you just expand out. So instead of this group squared, you would write that group out twice and multiply. All right, so now we're going to get into the locus. So don't be intimidated by the word. No, it's not the infestation. No, it's not the bug. Okay, a locus is just a set, could be points, could be people, just a set of data that satisfies a given condition. Like if I say, I'm thinking of all the even numbers, okay? You know all the even numbers, right? You know exactly what falls into that group. Okay, if I said I'm thinking of all the primary colors, do you know your primary colors? Maybe some of my art students do, maybe you're like, I have not a clue. Okay, if I said I'm thinking of all the students who have a 5th period class, that's everybody who has a 5th period class, right? But if I said I'm thinking of Miss Carrick's students who have a 5th period class, do you see how that narrowed it down more specifically? So that's all a locus is it's a set of data that satisfies a condition. Don't be intimidated by that word, okay? So this used to be in the geometry curriculum. If we had more time, if it was a block, this is when you come up to the board, we explore it through the geometry lens, but for our sake of time and not having you guys come up and social distancing, we're going to skip this part for right now. We're going to come down to the bottom. Okay, and this is where you're at home. You're going to actually be submitting this on Desmos, so make sure you're with me. So, sketch the locus, box it. Remember, all that means is data that satisfies the given condition. So the given condition, I can't spell. There you go. Put an H. The given condition is that it's equidistant, and that just means it's the same distance from the line and the point not on the line. So I want you to just start off finding one point. If you can find one, see if you can find two. If you find two, see if you can find three. What is a point? Now listen carefully. That's the same distance away from this line and that point. So for instance, one of the common ones that I see as people go down here. Is that point the same distance from this line as it is from that point? No, that one doesn't work. Okay, that's just a reflection. Okay, because this distance is not the same as this distance. Do you see that? Okay, see if you can find one point that would be the same distance away from this line as it is from that point. Give me one. If you come up with one, give me a second one. At home, this is where I want you to submit this on Desmos slide number 2. Give me something. I would rather you try and be completely wrong, but then understand what you tried. And again, without that submitting, it to Desmos, I have no idea where you're standing at home, what you understand, what you don't understand. Give me a point. Let's see if you can give me a second one. I like it. See if you can give me a third. I'm curious about this will have to be shorter. It's always interesting how much it varies from year to year.
Okay, so that's 2 points. But I wasn't thinking this way, I was thinking this way. Like this is the same.
When I like where your head's at, but when you measure to a line from geometry, you always measure down perpendicular.
Okay.
Like if I measured your height, I'm not going to start there and measure to the ground over here, right?
Yeah.
Whenever you measure the line, you always go down perpendicular. All right, thank you to the few people who actually submitted on Desmos. So clicking through, yes. Oh, what is the Desmos? Can I put the code? Yeah, absolutely. It's in the chat for you. All right, so let's take a look. So it's always interesting to me because it varies year to year on where you guys start. It really does. So what I've seen in person the most is people come out about here. Okay? The reason I said you can go out about there, do you see what shape they're creating? What shape is that? A square. Is that distance the same as that distance? I agree. Could I flip that over and do it on the other side as well? Do we agree that that distance would be the same as that distance if I created the same square on the other side? All right, I'm good with those 2 points then. That point right there and that point right there. Now, it's interesting because typically that's not where my students usually go. Typically, the one that's the first is this guy. If I ask you the same distance away from a line and a point, most people go right in the middle, halfway in between them. Are you okay with that part? Now, some of you tried to go out, and the question got brought up in class. When you measure to a line, if you don't remember from geometry, you always measure perpendicular to the ground. Like when you did those angle of elevation and angle of depression, right triangle problems in geometry. I know, I taught them. You always measure down to the ground. But do we agree that this distance right here is the same distance as that one right there? Check out what we just created. If I connected just those 3 points, do you see it? Some of you went further out with your points. Well, a rectangle might be okay, but that could be a compression if I went out further. But do you see how I created a parabola? This line, believe it or not, that every parabola you've always drawn, that line has always existed. You just didn't know it. That line is called the directrix. This point right here is our vertex of our parabola. And this point right here, which the whole parabola is bending around, and that point that it's equidistant from, is called the focal point or the focus. The directrix is the line. So I have directrix, vertex, focus. If it's easier to strip it away from the diagram, directrix, vertex, focus. Those are the 3 points we have to identify today. Are we okay with that part? Is it going to be the exact same idea if I flip this over and make it negative? Yeah. So flip the page. And I always have someone who asks me, Ms. Carrigan, when in life am I ever going to see this? Believe it or not, it exists everywhere. Okay? Magnetic force fields, believe it or not, are the connection of 2 parabolic surfaces. If I have a parabola and I have a parabola, it actually forms that ellipse. Draw a line right here. That's your directrix. Your directrix is like, did you ever play with magnets and you brought them together and then they rebounded away? Okay, that magnetic force field, the directrix is like our magnetic force field that's causing our metal shavings to bend in that parabolic shape, that parabola around, that's the parabola. Let me get a marker so that will show up better for you. So there's my vertex. That didn't show up any better. And the point it's bending around would be the focal point. And again, it works the same way if it's concave down. There's my directrix. There would be my vertex. There's my directrix. Remember, a directrix is like, in real life, that magnetic force field that it cannot cross. It's pushing everything around that focal point. the focus. All right, so if you look on the next page, this is the official locus definition. I'm not even going to read it, but we're just going to summarize that one more time. Focus, vertex, and your directrix, which is actually always a y equals equation. What you're going to learn in pre-calc is that this example can also happen to the left and to the right, but that's pre-calc. Okay, this is right now when x is squared, because it's our parabola. This you learn in pre-calc is y squared. It's the exact same concept, but you're just squaring the variable. X squared is a parabola, up and down, y squared is to the left and the right. All right, flip the page with me, because now we're going to get into it. All right, I've got one more last detail, so just stay with me for about 3-4 minutes, then we're going to get to the examples. All right, so the last part. Do you remember how I said it was equidistant? The distance from the vertex up is the same distance as the vertex down. Are you okay with that? That vertex up to our focal point is the same distance as the vertex down to the directrix. That distance gets the variable p. It is called, it doesn't make sense, it's Greek. It's called the focal length. I know, focal length, you'd want to use an L, but L is a different variable. The focal length is P, and it is always positive because it is a length or distance. If I handed you a ruler, you could never measure -2 inches because, again, if I'm asking you to measure a length or a distance, it's always going to be positive. All right, so the last part is, do you remember how we had those standard form? Y equals ax squared plus bx plus c, and we had vertex form, y equals a, x minus h quantity squared plus k. Do you remember how I said today was all about that a value? Here's the last thing I need to show you. How I'm going to calculate how narrow or how wide our parabola is. It's based on this p value. It's based on the focal length. Okay, the distance from the vertex to the focal point is actually what's going to impact how wide and how narrow. So our a value is equal to 1 over 4p. Okay, so 1 over 4 times the focal length. Or if I gave you the a value, the focal length is 1 over 4a. And we're going to use this, and you're going to see where it comes from in an equation. Please know you might want to just make this note on the next page because this is what's going to help you on a graded assignment. You can have the equation either in this form or in this form. And like I said, this is just the foundation. Pre-calcs where they really take it up another notch. Some pre-calc teachers show it in this form. Some pre-calc teachers show it in that form. It really just depends on your teacher. All right, so now what in the world does all this mean? Whew, I've been talking at you about 20 minutes. What in the world does all this mean? Let's start to connect it. Are you ready? So flip another page with me. So question number 1, are you ready? First thing anytime you have these diagrams, anytime you have these problems, you see these words, you should always draw a sketch first. So looking at this equation, point up if you think it's concave up at home, point down if you think it's concave down. Same thing for you this person. Do you think, looking at this equation, do you think it's concave up or do you think it's concave down? I agree, it's concave up. The reason I know it's concave up, remember how if the equation's positive, it's concave up? So if that A's value is positive, draw a sketch. But watch what I'm going to include in my sketch. Up until today, you never knew that every parabola you've ever drawn, believe it or not, has always had a directrix and has always had a focal point. You just never have found one before. I would label directrix, put a dot, vertex, focus. Directrix, vertex, focus. All right, so now looking at this equation, can you find your vertex looking at that equation? Just like we did in that warm-up. Alex, can you help me out? What would your vertex be? Opposite, same. Opposite, same. Opposite, same. Sorry.
-7, 4.
Beautiful. -7, 4. Right? Remember, -7, opposite, 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 same. Are you okay with that part? Now, remember how I said today is all about that A value, right? So that A value right now is 1/8. But do you remember the formula that we just wrote down to figure out A? A is equal to 1/4 times that focal length. Looking at 1/8 and 1/4p, I could set them equal and solve, but can anyone look at that and tell me what your p-value is? 4 times what? Gives me 8.
2.
So your focal length is 2. All right, so here's where it's going to, does everyone see where that 2 came from? 4 times what in the denominator will give me 8? 4 times 2, so that p-value has to be 2. So now here's where it comes together. You ready? -7, +4, label, that's my vertex. You have your vertex. Do you see what I circled? Because that's what I have in my sketch. Now that focal length, remember I go vertex up my focal length, vertex down my focal length. So if I go my vertex, if I go up 1, 2, what do I find? Is that my focus or is that my directrix? My focal point. That's my focus. If I go down 2, that's where my directrix is going to go through. So it's really about finding your vertex, finding your focal length, and then I can find my vertex and my directrix, my focal point, my vertex, and my directrix. So my vertex was -7, 4. I went up 2, so my focus is -7, 6. I went down 2, so my directrix is y equals, and the y value there is +2. Remind me, how did I get that focal point again? I had my vertex, right? I went up my focal length. That gave me my focus. I went down my focal length, and that gave me out my directrix. All right, let's take a look at another one. You'll start to see the pattern. So first of all, is it concave up or concave down? Look at number 2, concave up or concave down? Point up for concave up, point down for concave down. For those of you especially at home, up or down? Come on, what do you think? Up or down? Up or down? I agree it's up because, again, it is positive. Look at that A value. So I'm going to draw a sketch, always, including my directrix and my focal point. You should be drawing it too. You're with me on every step. What is your vertex? Mark, what would your vertex be on this?
3 and 3.
Beautiful. Vertex is 3, 3. I'm going to even graph that while I'm here and label it, of course. All right, now my next step, I can't find my focus and I can't find my directrix without my focal length. So remember, it's all about that A value. A right now is equal to 1/12. The formula for A is 1/4 times that focal length. If you can't figure out 4 times what is 12, could you set them equal to each other and solve? Yeah, but what is my P value? P would be equal to 3. All right, now here's the catch. I know I'm going up 3 and down 3 from the vertex. Are you okay with that? Up 3, down 3. If I go up 3, wait, am I finding my focus or am I finding my directrix up there? Vertex up 3. Okay, that would be my focus. So it's going to be 3, 6. And if I go down 3, good. It's that directrix, y equals 0. Questions on this part? Okay, I'm not giving you any additional homework tonight. We're going to pick up with examples tomorrow if you flip. Do you see how now I don't give you the equation, but we're going to have to write the equation? Okay, that's where we're going. Please make sure, again, if you did not take part 1 or part 2 of the test, you reach out to me immediately.